This ODE is going to be rather nasty to work with, but hopefully we can figure out the stability of all the equilibrium points without actually computing too much. So right here we have y prime equals y cubed times y minus 2 squared times y minus 3 cubed. At least the equilibrium points are easy to identify. Those are going to be at y equals 0, 2, and 3. And so hopefully we don't have to calculate too much. So let's say we started off first with just this f of y and partial derivatives approach. And to save you all the calculations, I just pre-computed everything already. And so it's a bit of a letdown if you actually go through these calculations. So if you evaluate partial f partial y at y equals 0, and at y equals negative 2, or at y equals negative 3, all of them come out with a value of 0. And because it's 0, it's not greater than 0, not less than 0, the stability of all these points is inconclusive based on using the partial derivative of f with respect to y. Alright, well that's not very good. So if we really wanted to, we could draw the direction field. But let's go ahead and try and draw the phase line with the graph to try and figure out the stability of all these points. So the first thing is, okay, well, it really only matters if it's positive, negative, or 0 on the graph. And then we're going to try and construct it from there. So let's say that we plugged in y equals 10, right? So that's far to the right of 3. 10 is much greater than 3. So here we get 10 cubes, that's a positive number. We get 10 minus 2, 8, and then we get that squared. It's always squared, so this is always positive. Then we have 10 minus 3 cubed. 10 minus 3, that's 7, cubed at positive. So it's going to be a really large positive number because we end up with positive times positive times positive when y is equal to 10. So from there, we know for sure that we're going to be up here somehow when we're to the right of y equals 3. Alright, so now we can go back to like, well, what's it going to look like when we get close to y equals 3? Well, near y equals 3, it's going to look like a cubic because this term is to the third power. So when we cross through the y-axis, the horizontal axis here, it's going to look like a cubic function. And so I'm going to try and draw that, so just give me a moment here. Alright, that looks okay. So it looks something like a cubic when it passes through y equals 3, and it had to be positive on the right. We tested it by just plugging in y equals 10. Alright, at the next point, we have y is equal to 2. That has to look like a parabola when it gets near the root, near the equilibrium value. And so if we're at y equals 2, it has to look something like a parabola, so it has to do something like this. Alright, so that's y equals 2. Then eventually we're going to get to, let me just write that in. Eventually we're going to get to y equals 0. That's going to have to look like a cubic again. So in order to look like a cubic, it's going to have to cross somehow like that. Not the best graph drawing, but it got the job done. And that's y is equal to 0. And now from here we can determine the stability of all these equilibrium points. So let's go ahead and draw our arrows. Right, it's positive on this side, positive slope, negative slope on this side. So the arrows do something like that. Then something like that. Right, negative slope. On this side is also negative, so they're also pointing the same way. And on this side, it's positive again, so those are going to point to the right, and they'll get bigger and bigger as you get further away. So we have 3 equilibrium points here. Since all the arrows are going away from y equals 3, that's going to be unstable. In here, we have semi-stable, so I'll draw my circle, and it's stable from the right side, unstable on the left, and this point ends up being stable, y equals 0. And you can also check that the stability has to flip as you go through different adjacent equilibrium points. So this one's unstable. If you keep going to the left, you'll end up on the stable half of this semi-stable point. Then you have unstable on the left half, and that is adjacent to a stable point, so it's flipping as it's going through. Alright, so from here we can actually figure out the stability of all the points here. We can also figure out now whether the slope fields are going up or down in all these regions. And so above 3, based on this graph, right, if we're above 3 we have positive slope, so we should have positive slope up here. If we're a little bit less than 3, so between 2 and 3, we should have negative slope, so something like that. But then if we're between 0 and 2, we also have negative slope, so something like that. But then if we're less than 0, we're going to have positive slope, so something like that. And if we're to graph those solutions, right, so solutions here will do something like that. Here they'll do something like that. Here they'll do something like that. And then here they'll do something like that. And right, so based on these, we can also tell that this one is unstable. This one is semi-stable. And to draw that in, right, like that. And then the bottom here is stable. And so there you have it. When you have these inconclusive points, it doesn't necessarily mean that it's going to be a semi-stable point. It still can be stable and unstable. It's just usually the powers are too high to figure it out. It's kind of like in calculus for determining maxima and minima and inflection points. Sometimes the tests were inconclusive and they could be either one because the powers at that point were too high.